sort of the context for FlureeDB is enterprise software. Our last company was Silk Road Technology. We're a large software as a service provider. We grew that company to about 500 or so employees. And before that was a company called Divine Interventures. We were actually the very last company to go public during the .com bust, right as that was sort of happening. So not ideal timing, but certainly a good experience. So yeah, enterprise software for a long time, and that's really what led us into this particular space. So we were definitely very excited by the potential of blockchain and how it might impact business, understanding the business software side. And one of the things that we had often found frustrating in the other companies that we had built is that as you're building a company, you're acquiring or kind of building more and more software, always pursuing kind of the suite model. Yet the marketing message of buying a suite versus everything actually working well together always sort of falls short. It's always like you're trying to play catch up. So we really wanted to come at this to leverage some of the new technologies we saw coming out today, like containerization, like blockchain, and see if we could develop a whole new technology stack that, in a perfect world, sort of you build microservices and they just kind of magically integrate and everything just sort of works, and you no longer have to go to a Salesforce.com because any company can publish little modules and you can assemble them together, and the world's sort of perfect. We've actually built a prototype of that entire stack, and it ends up really consisting of two parts. One, which we won't really talk about today and have decided not to focus or try and release for a while. We call it the App Factory. So it's really a microservices, serverless kind of container, wrapped around container platform. And the reason is because the underlying piece, which is the database, for one, it's turned into a really big project, and there's just been a lot of interest in it. So this is really where our focus is, but really our goal is ultimately to really enable companies to deploy and leverage what we loosely call decentralized applications. And we think that kind of this is really going to be the way things head in the coming years, 5 years, 10 years, I don't know, but certainly where it's headed. So FlureeDB is a blockchain database, and it really it marries those two concepts together. How we built it is that we wanted to be the easiest and most accessible way that a company can leverage blockchain technology within their apps. And so that sort of implies that the current blockchain technology that is out there is difficult for companies to use, and we definitely believe that. It's very hard to fit into the stacks that you're currently working with. There's new programming technologies, the talent's really scarce, and the idea is, what if we could bring some of the blockchain characteristics to a core part of the application stack that people already know. Everyone sort of starts with a database and knows how the database works. And then the second part of it is, how can we actually leverage some of the technology that's available today to make a better database, a database that we wish we had. Really the presumption is there that the current databases don't really keep up with modern technology, and I at least believe that's true. The relational database has been around now for about 40 years. It was based in an environment where things like disk space was incredibly scarce, memory was incredibly scarce, and there's a lot of design decisions that went into the database at that point to deal with those constraints that really have for the most part carried through to today. So we're really still interacting with most databases in the same way. So the idea is to bring both of these together, and really for us they're kind of two sides of the same coin. So we already have people leveraging the database who don't even necessarily care that much about the blockchain side of it, but they just think it's a great database, and hopefully I'll get a chance to explain some of that here as we go through. And then we also have people who are really just focused on the database side. How do I enable some of these decentralized applications, concepts around smart contracts, etc. But they don't necessarily or aren't as focused kind of on this half of it. So a couple of things, at least on the blockchain side, that the solutions and really blockchain in general brings are this concept of extreme tamper resistance. So not necessarily tamper-proof, as nothing's technically tamper-proof, but tamper-resistant. The idea of these immutable ledgers that are cryptographically linked together. And you can't really alter history, because if you alter history, it's detectable, and sort of everything after it becomes, also would need to be forged or faked, which makes it incredibly difficult. And really this concept of consensus, the idea that you can run something, a blockchain, across multiple parties where nobody controls it. So it's run by a set of rules. I was just at a group the other week, Satoshi Roundtable, and one of the things they had up is the big banner as you come in is in code we trust. And the idea that sort of you code the rules, everyone understands exactly what it is not subject to any human being sort of getting in the middle of it or having an interpretation of it or anything like that. And certainly blockchain brings this concept together. One of the things that we set out with this project is that there's different blockchain technologies that are targeted towards what we call the public blockchain space. So this would be certainly Bitcoin is one that probably everyone's aware of. But Ethereum, how many people know Ethereum? Okay, good amount. So Ethereum, for those that don't know, is really a way of, unlike Bitcoin, which is just about transferring coins or from one person to another, Ethereum allows you to actually write custom code in it. But again, it's still sort of focused on asset transferring. So the custom code might be things like, hold it in escrow, and if these conditions don't happen within 30 days, have the money revert to this account. Certainly you can't do something like that with Bitcoin, but Ethereum brought that idea, and they have a programming language in Ethereum they call Solidity that allows you to basically do this sort of business logic. Those are public blockchain technologies. So they run the miners, anyone can mine them, there's no control of it, again, sort of the pure code. Things like IBM's Hyperledger Fabric is an example of more what we would call a federated blockchain. It's a blockchain that isn't designed to run publicly. There's no like coin you can buy or anything like that. But it runs across multiple organizations, and it is used to basically control some sort of rules that none of these companies, in theory, directly control. And one of the things we set out to do sort of with this database is we wanted to be able to support all these modes and support all these modes simultaneously. So we do have this notion we call hybrid consensus, where you can take a database, like a database that your applications are going to go talk to, but where that parts of the database data are being transacted might be in completely different places. So essentially we have a query engine that allows you to do joins across multiple databases. So some database data might be on the full public cloud, public internet, like in Ethereum, Bitcoin. Some of it might be data that that's among your supply chain network in sort of this federated mode. And some of it you might even just be running internally. And from your application standpoint, it can pull all this together and present it in a unified way. So certainly immutability, consensus. And the other thing is we took an opportunity, we said, well, as long as we have all this data and we're leveraging new technologies, what can we do to improve the database experience? So a couple concepts. One, we decided that definitely a graph database for us, we felt married where applications are today and where they're going and the easiest way of getting data out of them. So we definitely like that format. And as long as we are keeping this immutable ledger of all the history of everything that ever happened, how do we actually empower people to leverage that data? So we have this notion of, which you'll see, this notion of time travel built right into the database. And really the trick there is to make this happen really, really fast. But you have every single version of the database available to you instantly. So just like any database, you issue a query, it'll return the results, but it'll return them as of what I currently understand, here's your results. That same query, any query in fact, you can issue at any point in time in history up until the very beginning of the database, and you'll instantaneously get the results of the data at that time. This allows you to build apps that you can basically rewind with no additional developer effort into it. It allows an extreme amount of auditability to the data as you're centralizing it. And I'll talk about it a little bit more. We actually have a notion when you grab a database, it is a fully immutable database. So for those that do development, things like race conditions due to database data changing underneath you as you're processing transactions completely go away. Because when you do grab an immutable database, it will never ever change. Yes, sir?
How does that deal with just the amount of data? I mean, because you're multiplying the amount of data, basically.
Yeah, so the question, which is a common one we get, is isn't that a lot of data to store? And the answer is, yeah, sort of, but disk space is so incredibly cheap now that holding an extra terabyte of data, which is just a mountain of data, might actually end up costing you $1 a day. And the value of having that and having that history and being able to prove exactly what happened at different times is generally worth way more than $1 a day. You know, and that might be an extreme example. A lot of apps don't even need a terabyte. Some need multiple terabytes or petabytes. One of the things that we target this database for is application style data. So we're not trying to sell this as sort of this massive data warehouse. There's a lot of tools available for that. And you should use those tools. We're really looking at this database backing applications or things like that. So we're generally working in a world, or at least the guidance we give is, sub 1,000 transactions per second, which fits every app I've ever worked on, but fits 90+% of applications. But if you have something that's massive volume, there's other solutions out there for it. Or again, if you're just trying to build this massive data warehouse, you might want to go for a Hadoop or something like that, because that's kind of what they're designed around. Yes?
So, I mean, it seems kind of obvious that you guys probably have some way of mapping traditional database entities, or maybe it's nodes and edges, since you're GraphQL, mapping those into blocks in the blockchain. Is it okay to think of it that? Is that too naive of a
No,
of a
it's not. So the question is, are we mapping essentially edges and graphs or edges and nodes into a blockchain or a ledger format? And the answer is yeah. And I'll actually show you that here in a minute, so it's a good lead-in. One of the things, just to get sort of a visual as to where this particular solution fits into a typical application stack. While you don't have to run it this way, we have set it up so that it can really thrive in a CQRS sort of model. The idea that data flow is always going only in one direction. It's never going back and forth. You don't have to do it that way. But you still have a business logic tier. So this may be your typical app server. You're writing something in Java, .NET, whatever. It's doing whatever it happens to be doing. This could be one of the current cryptocurrency solutions that's performing some sort of smart contract or anything like that. Really, wherever you're looking to do a business logic, that piece fits in. Where we really fit in is, again, at that data tier. And one of the things we've done in this process is we've really deconstructed the database. So, everyone thinks about a database as this thing that you go, you talk to, gives you answers, you send some transactions to it, gives you an answer. And we've actually separated the database out so that things like where you go and ask questions, simple from an app standpoint, is actually different servers, different processes than what's doing the transactional part of this. And this allows the transactional part of this to exist in this blockchain sort of world. So basically, what we would call the miners are just running the transactional piece of this, the changes, the deltas, the state changes of the database itself that the transactor executes. It's automatically feeding that data out to the query engines. And the query engines are eventually consistent, and that's what your app is hitting. So in order to run this, for example, in a fully public model, say you're setting up a database that a bunch of miners are working on, and you have this data, you have these rules that govern how the data can work and get updated. That all sits somewhere in the cloud. You still need to run a query engine, and that's what your app's talking to. So you don't necessarily have to be running a transactor because you may be having other people transacting the data for you, or you're in this consortium of companies, whatever the case. But your app that's trying to get at that data would talk directly to a query engine. And I'll explain this a little bit more. Yeah?
So in a Ethereum type of a blockchain, there are thousands of nodes.
Yeah.
And there are different miners who are running those nodes and operating things on there. So is this database running on all those nodes, or is it running outside that?
Anyone, so actually every single database in our world is actually technically a different blockchain. So it's really the side chain sort of model. So there's a main backbone chain that's keeping the integrity of everything. But every database is its own essential side chain, which allows miners to actually decide what databases they're going to mine. And the reason to decide whether or not to mine a database is how much are they paying me to essentially keep this data live, and how many transactions are they processing, because I'm making money as I'm processing transactions for them. And if the economic incentives aren't there, you may choose to not mine that database, and that sidechain database, it's possible, could disappear because no one's even maintaining it because there's no economic incentive. The cool thing we see for this is the idea that there may be some altruistic sort of databases that people want to run in the cloud. Maybe it's something, United Nations has a new project where they're trying to track global climate change data. And of course, all the controversy right now is that certain governments are hiding some of the data and whatnot. But here's potentially a way that United Nations might publish all that data in this global public database. And maybe they provide zero economic incentive for people to maintain it. But I believe in that cause, and so I'm willing to mine that for free. But maybe there's another company over here that's running a database for some profit reason, and I'm not willing to run that for free. But as long as they're paying me enough money or I'm making enough on the transactional side, I will mine that database. But we see this notion of kind of these global databases that no one controls that might be tracking the human genome or things like that. And of course, there's all kinds of commercial purposes for all of this as well.
So the buyer for this technology would be miners, or would be any developer who wants to create a blockchain technology?
Both. So that's really where we kind of we designed it in a way where we wanted this to work in a full public blockchain model. So really the miners are the ones making the money, and the people paying the money are the ones who want to have this database maintained in the cloud in this blockchain-centric way. But you can run this in what we call the federated mode, where you're just running it amongst a consortium of companies. You can actually just run this, throw it up on your laptop, and run it completely private. Now, of course, what you're giving up when you run it private is you're giving up essentially this notion of consensus. But as I'll explain, there's still some benefits of doing that. And you still get some of the characteristics. You get a really cool database. And if you're running this in a way where you actually have a whole set of data for an application, some of it may be in the public mode, some of it federated, and then there might be some set of data that you don't want in either of these places, but you want it internally. Maybe your employees' addresses, right? And maybe you're running with your payroll system or something else, how you're paying those employees, but you don't want that extra personal information to go over to that network. You can actually run that internally, and at the query side, we can actually join all that data together. So from your app standpoint, it looks like it's one database, even though different parts of the data are getting have different levels of consensus around it.
Question.
Yes.
So does your eventual consistency in the database come from the consensus model of the blockchain?
Yes.
Okay.
Yeah, so the question is, does the query engines are eventually consistent. We do give you an option to force consistency around certain queries if you want. But does that come from the, if I understood it correctly, does it come from the consensus model or the transactor? And the answer is yes, and I'm actually going to walk through that right now.
Is there a minimum number of nodes needed to do the consensus?
It depends how you're trying to accomplish consensus. Technically, no, but at the point there's only 2 nodes, then
It's like very lame.
yeah, you said lame?
Yeah.
Yeah, it's lame. Yeah, that's good. I just want to make sure that's what you said. Yeah, yeah, that'd be pretty lame. Unless you're playing around with it yourself or something like that.
Well, it's scalable
Yeah.
all the way down.
Yeah, I mean, you probably, for having real good consensus around things, at least on the public side where you don't trust the miners, you probably want something in the area of 1,000 plus people actually maintaining and mining that. Because you don't want it to be easily overwhelmed, the network to be easily overwhelmed. And we could talk some about the public consensus model. We have not launched the fully public version of the database. We have a launch of Q4 of this year. But we can talk through, so that full consensus model isn't fully out there yet. But I'm happy to talk through how we're doing that.
I'm curious about the queries on the database. Are they basically coming from the Ethereum programming language? So are we embedding the queries in that smart contract?
No. So really, so the question is kind of where the queries are coming from. Is the logic based in a smart contract? And the answer is no. Really, this has nothing to do with smart contracts. But the idea is that if you want to design a schema where you're housing a lot of data, then this would be a really good place to potentially put it. Something like Ethereum is an awful place to put a lot of data.
You can't because it's so slow.
You can't because it's not only so slow, but at least my last calculation, which is outdated, I know it's more than this now, to store 1 gigabyte of data on the Ethereum blockchain. And you're running a supply chain network against around 10 companies. You'll hit a gigabyte of data really quickly. 1 gigabyte of data on the Ethereum blockchain would cost $10 million US.
Whoa, are you kidding?
Yeah, but to be fair to Ethereum, it was never designed to house data. It was only designed to do really these smart contracts in sort of transferring one asset from here over there. So and it does, well, they would say they don't even think it does a great job of doing that yet, but of course they're working there, and it's one of the better solutions out there right now to do that. Yeah. All right, so I'll walk through a little bit sort of how the data is structured, and I think it answers the eventually consistent question as well. So really we're just storing tuples of information in a log format, and it's really just an append-only log. I mean, it's a pretty simple format. We store enough data to do some really interesting things with it, which hopefully you'll see. But what we start with, and we'll focus here just on the transactor. And again, the transactor, the only thing it's responsible for doing is transacting. You're not hooking any apps. No apps are trying to talk to it or anything like that. It is just running the blockchain network. So your app is going to be talking to the query engine we'll talk about in a minute. So say a transaction comes in, and everything is in JSON format with us. We also support GraphQL if people use GraphQL. But here's a very, very simple transaction for the ID John, and that's a simplification. But whoever John is, that entity, I want to update John's email address to be john@Fluree. So that's a very simple transaction. This would get signed, and you send it basically to the network. The network, again, could be it running on your local laptop, or it could be the public network. That ends up, if it's successful, based on rules, we actually have a programming language that can be embedded right in the database. So we'll talk about this. It allows you to create very involved rules as far as who can update what data and exactly under what conditions it can get updated. And this is what allows these to run in a network, that these rules are already encoded. So basically all the permissions of the database are encoded right in the database. Actually as programming, but the programming is just data. So everything that runs the database is actually just data in the database. So assuming this is successful, it will end up creating a new block, and that new block has a whole set of data with it. This is an abbreviated one that only highlights exactly what we changed, but in this case we updated John's email address from Johnny@Fluree to John@Fluree, and this essentially creates 2 entries in the log of the blockchain, assuming it's successful. So it's saying, John is entity 123, we're updating his email address. This is the old value. We're removing it at this point in time. We're essentially saying this is no longer true. In this case, we're in the exact same transaction. We're actually creating a new one, which is we've updated his email address and we're saying it's true. And again, all this is linked to a block. And as you'll see as I show you some demo, there's a lot of other block metadata that also gets into this. But at its core, this simple transaction results in these 2 log entries, and that is the only thing we need to make all this kind of magic happen. And then looking at the query engine, basically what the query engine is, again, it's somewhat simplified, but here's our last 2 entries that just came in block 23. There was a previous transaction, block 22. There was a previous transaction here, block 21. Every one of these essentially creates a version of the database at a point in time. Now, we don't actually store all these versions of the database physically. There's a lot of, we're using, in this case, functional data structures to actually share a lot of this. So it's very, very fast to get to every single version. But every single version of the database is available to you. So if you want to issue the query as of block 22, of course it's going to ignore anything that happened after it. And it's only going to take into consideration everything that happened up to that point. And this is one of the key ways we let you leverage this historical data, since we're keeping it anyway and we're spending the money for the extra hard drive space. Let's help you actually take advantage of it and do some interesting things with it. But yeah, this core data is all we need to put in here. There's, as I mentioned, there's a couple other pieces. Every single block has a bunch of metadata that gets created with it that creates the hashes, links them to the previous block, makes sure they're immutable. There's another piece of data we don't show here. Every one allows a notion of expiration. So when you transact that data, you can say, expire this in 7 days or 7 years, and that data will actually end up dropping out of the database. And if anyone cares to get into it, we still have a way of maintaining, even if data disappears, we have a way of maintaining the integrity of the blockchain, just using a version of a Merkle tree that we have. But yeah, essentially that's it. It's an append-only log. Really, really simple. Now, I will, it's not mine.
So I guess based on that last slide, you could say that for any block ID that's already tripped the consensus wire, it's forced consistency. Like if do you specify in your query which block ID to look at? And
you can. You can optionally specify. So if you don't specify what point in time you want an answer to a query about, it'll always by default say, based on where I'm currently at, here's the answer. You can specify a specific block that you want that query returned of. And that block can actually be in the future. And what it will do is that if you just did a transaction and it said, okay, we're now at block 100, and you want to turn around and issue a query, you can say, just don't even give me an answer until you're at least caught up to block 100. And then it will wait if it hasn't quite been synced to that point and actually send it to you at that point. So you can force consistency in the areas, usually when you want to do that is I issued a transaction, I want to immediately turn around, issue a query, and maybe it's hitting a load balancer and there may be 100 query servers running. And every one might be getting synced at a different millisecond, and I just want to say, hey, unless you're at least at this point, don't give me an answer back. We could not get me internet access, so this is my qualifier. I'm running it on my cellular network. So if it seems a little slow, etc., that's my excuse. Okay, so what we're looking at, and I'll try and zoom this up a little bit. We are looking at an admin panel for FlureeDB. So we currently have a beta version available where we're hosting everything, and anyone can sign up. And essentially, we manage the infrastructure. You would typically be issuing the type of queries we're going to issue and doing all this, obviously directly from your applications. But this is just a way of interacting with the database through a UI, and we have a quick start guide that kind of allows you to go through some sample transactions and schema setup. But I'll walk through just kind of real quickly what we have. You can interact with the database in two main ways. We have a GraphQL interface. If anyone's currently using GraphQL, if you're not, we wouldn't probably recommend you use that because it has some limitations. We can do more things with the database than we can sort of force GraphQL to support. And then we have our own way of querying it. We call it FlureeQL. And the goal, at least for the basic FlureeQL, is that we make it very SQL-like, but it's all JSON-based. The cool thing about having your queries in something like JSON as a data structure is that your code can actually really easily manipulate queries. It's not like you're trying to like concatenate this big string in this specific order or anything like that. So one of the things to give you a sense of what your database looks like, and I'll use it here to show you what we're going to be querying and interacting with. We have added these, we actually call them streams because they're these continuous data streams, but you think of them as tables. We have 3 tables we're going to interact with, I'm going to query. We have a simple chat app. So this chat has the chat message. It actually has a reference to the person that made the chat message, who authored it. So our person table over here, we store the instant and time it happened, and we have a reference to potentially multiple comments. If people leave a comment, they can leave a message, and of course every comment also has an author, which also points to the person. And the person's pretty simple. We're really just storing their full name and their handle. So just something really easy here. And let me see how big I can get this here. All right, that probably work. Hopefully everyone can see it okay. So this does hopefully what you would expect. Select star from chat. And we're going to return all the chat messages currently in the system. And what we see here in the results is a couple things. Of course, we have the chat messages coming back. They actually come back in the data structure. And in fact, I'll get into it in a minute. You can structure your select syntax where it actually represents the structure of how you want the data back. So of course, when we build front-end apps, we're really used to using database drivers or libraries on the front end. And a big role of those is kind of destructuring the data or putting it into usable data sets. Because we're using JSON here, it just comes back that way. That's not to say you wouldn't necessarily still want to use a database driver in your front-end app, but you can describe how you want the data returned, and we automatically return it in this nested graph format. Each one of these objects essentially is an individual entity. So here's a chat message. It says Zach's message. In this case, it actually refers to Zach as a person. But again, because we didn't ask it to follow the graph through to the person, this is basically a database join. It's just showing us, hey, this refers to this other entity here. But you didn't ask us for any of the data. And I'll show you that in a minute. It also says what we know about the database right now, because we didn't specify a point in time, is we're at block 20. So it's just letting us know, just this is the moment in time. That block 20 database, if you wanted to turn around and issue more queries, it will never ever change. This query will always return the identical results throughout the history of time as of block 20. And then we return a couple other pieces of information, like the time it took to execute the query. So this query went through and we returned this data in 1.2 milliseconds, et cetera. But just a little bit of information. So if we wanted to leverage some of the crawl the graph, so to speak, has anyone used something like Neo.j4 or anything? Neo4j. Or Neo4j, sorry. Yeah, so we tried to allow you to actually just describe the relationships right in the query language, and at least in my opinion, it works pretty well. I think it's an intuitive way of using a graph database. There's sort of a learning curve that certainly I've gone through, and others that I hear, as far as how to structure queries and navigate the data. But what I'm going to specify here is basically just a query inside the query. So what I added to this query is that in addition to sort of select star from chat, I'm going to add another thing here, is actually follow this chat person relationship and then select star from there. And again, the description of your query is really exactly how the data comes back. Right. So now I'm pulling out those additional details about who it was, etc. Every time you form a relationship in the database, so obviously here there's a relationship from chat messages to people, those relationships are automatically formed.
Yes, you're done.
In reverse.
Somebody has hacked the IoT blockchain here. I think their database says that they have to send those up at 8 o'clock. I've seen other companies do the same thing. They've probably also turned off the AC and shut off the air supply.
Yeah. If anyone has any, until we get back to any just even generic blockchain questions, I don't know. Obviously, all the projects, there's thousands of them, but I'm happy to answer what I know. Yes.
Well, this is not a blockchain question, but how's the time travel different than a traditional database in terms of what you could get from you versus something?
Yeah, so the question is, how's the time travel different than a traditional database? And there are some databases that do try and focus on time travel sort of first, and there tend to be time series databases. They tend to be very difficult to query because they're sort of focused around that dimension. There's databases like Oracle, which has a feature that allows you to get different points in history in the database. However, Oracle recommends that you only turn it on because it's very intensive the way they have it implemented. They recommend in the time frame of hours to maybe days of historical data, but you don't really have it beyond that. Really the core here is that every transaction is a moment in time, and you have every version throughout the history of the database. Yeah. So using, I guess, the top, 5 databases that are probably in use today, I'm not aware of any that support it.
Just need this on, right?
Yeah. Yeah.
So I've actually got a bunch of questions that I'd like to get a mindset of the general question from asking, especially in your CRUD. Does your access control only relate to create, update, and destroy, and not read access because the blockchain and all of your data is public?
Public.
Okay. And so there's
that's not that
access control.
No, I haven't answered that yet. But yeah, I was just confirming what you were saying. So the question is sort of does the permissions, and I haven't shown yet, you can actually embed just simple predicates or also more complicated predicate functions that determine exactly who can write data when. If this is in a full public blockchain mode, then read access, everyone can see it. It's a complete public blockchain. If you're running it in private or even in a consortium and you're keeping the query engines outside, that your apps can access the query engine but they can't maybe access the transactor, we actually allow those same programming constructs to be used to control read access as well. But in the case that it is a full public blockchain, then everyone can read everything. So it's only in sort of the federated or private model that the read access comes into play.
Okay. So conceptually, the problem that I have is that all of your access control has to be...
This just takes a minute, I think, to warm up and pop on.
Okay. All of your access control has to be processed by all of your minor nodes.
Absolutely.
That are processing your blockchain.
That's right.
They have to go through all of the rules. They have to...
Yep.
And now the other thing is that all of your time machine and consistency and the ability to read to any block back in history is that I need to contain that entire ledger back to time immortal, right? So how big does your blockchain get?
So this is the same question that really came up earlier, is that because you're storing everything, isn't that a lot of data? And in some applications, if you're trying to create a massive data warehouse for Walmart, then yeah, and this isn't probably the database to use. So our target here is really enterprise applications. And in that context, most enterprise applications, the amount of data that accumulates is cheap and within realm of storage. So, but that is one of the decision points that you would have to make if you were looking to deploy this, is how often is the churn of updates, and how much is that going to accumulate. If I got something like a simple counter, the amount of data that's accumulating is quite small. But if I'm trying to store images and I'm updating images every 2 minutes and these images are really large pieces of information. One of the things I like to bring the parallel, because there's a lot of parallels to something like Git. And if you talk to people about what Git really does, this same question seems to always come up. It's like, wait a minute, every single change in my source code throughout history?
No, Git is different, and you may be differential as well. I mean, the differential data change is what...
It is. Everything that I'm showing you here is just deltas.
Okay, but now it seems like the plausible performance and data size is a matter of each of the nodes respecting the access control of the data, and you don't have any malicious participants in your blockchain.
That's where the consensus comes. So every node is running the identical rules. And if I am the node that gets to process this transaction, when I broadcast that transaction to the network, it is in fact true that everyone participating in consensus, if they're doing their job, has to also process that same transaction. The only thing we really need to compare is the resulting hash, because if the hashes are the same, then we know we came up with the identical results. But we all need to go through that process. And in fact, Ethereum works the same way. So in Ethereum, there are tens of thousands of miners. Every miner that's participating for every transaction is spinning up an Ethereum virtual machine, running all that application code, getting the results, and then comparing it to what you told me the results were. And I vote, essentially. I say, yeah, I agree, or no, I don't agree. And the point, if there is one to all of this, is that with today's computers, with the memory so cheap, storage so cheap, you would be amazed at what we can do very, very quickly. But yeah, everything is there, which is the point, that we have everything. Yeah.
I'm not sure if I misunderstood or not. Did you basically just say that your consensus algorithm is all the nodes verify that the access control rules were followed?
Yeah.
I mean, it's not proof of work, right?
It's not proof of work.
It's something else. Is it proof of?
Yeah. So you have to do two things. So you have to verify that the results of what someone else said the result of a transaction is the same that you came up with, and then that other person who was elected, essentially via, you can think of it as a proof of work sort of algorithm, also had the right to issue that. They solved the puzzle. They had the lottery ticket that won the right to issue that block. And Ethereum works the same way. So there's two things you have to do in Ethereum. One is you have to solve proof of work to get the right to mint the block. The second thing is then you have to process all the transactions that you decide to include in that block, and everyone needs to agree that those transactions, when you broadcast them out, that, yeah, that's what they got too. Identical process. So two things. Successfully and correctly process the transactions and win essentially the consensus algorithm.
So there is a proof of work element too.
We don't use proof of work, but and we can talk about that more. So we use a concept of proof of capacity, which is very, very similar conceptually to proof of work, but there's some different characteristics, and I'm happy to get into that
Actually,
later.
I mean, what we probably care about is scalability, so how it impacts scalability.
Yeah.
Is really what I was asking.
Yeah. Someone else have a question? Okay. All right. So what I was about to show, was just a quick feature of the graph database side. So, we followed the graph, we selected all the chats, we followed the graph into person. But again, anytime you set up a relationship, that relationship always exists in both directions. So if I wanted to, in this simple example, instead of finding the chat messages and showing the people, if I wanted to flip that around and say, well, what chat messages do individual people do? It works the same. So instead of selecting star from chat, I'll select star from person. But I'll follow the same relationship. Again, it exists in both directions. I just need to indicate here that I want to follow it in the reverse direction. And I'll go ahead and invoke that. And what we've done is we've just flipped the data over. So now our results are actually the people we have in the database, but we're actually showing all the chat messages each of those people have done. And these graph relationships can be followed as deep as you want, and something like even infinite recursion is something we just naturally support. The database is happy to be in that sort of world. So if you had a situation where, for chat person, I followed you, but you followed me back, and we say infinitely follow these relationships, that is a perfectly valid query in FlureeDB. Of course, internally, once we see sort of the same entity more than once, we'll cut off the tree, so it's not in an infinite loop. But you can follow these recursive relationships that might even point through, 3 different sort of tables, and then loop back and point through 3 different tables, and that's perfectly fine. It's happy to have those, and it can exist in that world. Okay, so I'll just come back to this real quick, which is my last query. So here we're listing the chat messages, we're listing the people. Now say I want to update a message, and I'll update Zach's message here. We issue a transaction. Transactions are pretty simple. You can just use the internal ID. So here we'll use the ID of this, but you can also use any attribute that's used as a unique identifier. So if you don't know the ID, you can just use any attribute that's a unique identifier to say, figure out this entity or resolve this entity. But we'll update this and we'll say that all right, and so that that transaction successfully happened. I'll go back and requery the data so you can see that, but I'll explain this for a second. So here's the result of a transaction. One of the things we do is we actually map, if you used any unique attributes or you used a temp ID, we'll end up returning to you a map of the temp IDs or what real ID they resolve to, just in case your app needs to know, hey, what ID did the database end up giving this entity? We end up giving you the final hash of the block. Here we're now at block 21. We're saying we've got another block in place. And here's actually the flakes. I didn't specify that before. Each of these kind of log items, we call them a flake. Here's the flakes that were changed. So this is the delta. This is what was changed in the database. The state change in the database, nothing more. But this delta creates a new version of the database. And you see here that we had Zach's message, which is what was in there before. We set it to false, meaning it's no longer true. And now we have Zach's updated message. We set it to true. And this, again, is metadata for block 21. So these are the hashes, the previous hashes, the point in time that this particular thing happened. So again, we change it to Zach's updated message. We'll go back to here to this simple query. And of course, what we see here is Zach updated message. Now, to bring in the time travel, we'll also see up here at the top that we're now at block 21. Before this said we were at block 20. So again, you can go back to any point in time. So I'll just append here that I want to issue this as a block 20. And there's Zach's message. So this block 20, this version of the database, again, will never ever change. It will always provide these same results. I mentioned before, race conditions for the database really completely go away in this model. Things like, I'm running some backup process at midnight and it failed, and I get in at 8 a.m. and I need to figure out why it failed. Well, lots of times that's hard because data's been changing and I don't know what made it fail at 8 a.m. I can get the exact version of the database that whatever happened at that point in time and actually figure out what failed, why did it fail. Everything's always there.
Can you get a list of what would have been Zach's messages, including the one that's no longer showing, or could you query by a time to get what block it is?
Yes, so the 2 questions. One is, can you query by time? Yeah, so we support not only the block number, but you can supply any wall clock time. So any ISO 8601 formatted string for time. And under the hoods, what we do is that because every block we also encode in the metadata, the moment in time it happened, we essentially figure out what block we were at that point in time and then run the query for that block. So yeah, you don't have to specify the block to go in history. You can specify any point in time in history. in your other question, or was
So
that?
you could just query for all of a person's messages, even the ones that before it was updated.
Absolutely, and so I don't have it in this UI, but there is a API interface that allows you, every piece of information here, we also have the exact block that this piece of information happened in, and we can show you every point in history, everything that happened to that piece of information. And we may know that this piece of information came in at block 8, this one was at block whatever, and then what you can also do is you can say, okay, I know that this here was set at block 8, what else was set at block 8? Who did it? When did it happen? So I can leverage that block 8 and actually answer all those questions. What else was changed at that moment in time? Who did it? And when?
So your SQL query engine will run a consistency level at a particular block backwards or forwards to do your time machine function.
Yes.
And you could run flags backwards to go back in history. When you start up a node, you have to ingest the entire chain and build your consistency model to a particular end block, right?
You don't. So the question is, when you, at the transactor level you do. So at the query engine where we're issuing these now, you don't. The question is, when you start it, does it need to fully ingest the data? And the answer is no, because actually all this data, and the reason we can do these queries so quickly is obviously we're using indexes underneath. We borrow some inspiration from Cassandra. We write out these immutable index segments that can actually be shared across your query engines. And we actually allow, we're sort of running this as an in-memory graph database, but what it is swapping underneath as it basically doesn't have enough memory is it's swapping out actually immutable index segments. So all the indexes that are allowing all this to happen so quickly are all pre-compiled and sitting in there, and they're shared across the query nodes. So when that query node comes up, it doesn't have to load a thing. It's available to answer a question instantly. As soon as you ask it a question, it will start basically crawling down, depending on the type of query in the index, it'll start crawling down the B tree and say, oh, I need this node, I need this node, I need this node. And it will go to its peers and actually get those index segments, quickly pull them in, and turn around and answer the question. And from a cold start, generally, most queries will respond within 50 milliseconds, and you'll see as we go through these, most of these queries will respond oftentimes sub 1 millisecond.
And when you do that, build those additional, are those built as additional flags that are built?
No. The only thing that's needed,
with the consensus model?
because you're running your own query engines at that point. So your app is interacting with your query is getting that log file feed from the transactor. All I need to do is get that log file feed. From that log file feed, I can build all the indexes around it, and I'm running all that locally. So you're running your own query engines. The cloud isn't running your query engines for you. It's only running the transactors. The transactors are just giving you updated log files. The query engines are receiving that. They're talking to each other, and they're basically creating new indexes that they can all share so they can respond to queries very quickly.
I think, okay, I'm confused. It still seems to me that at point 0 you have to ingest the entire data in order to build back those indexes. Or send the indexes through the trust consensus model.
A transactor would be the only thing that would be required to do that. But the query engines, again, they're yours. You're pointing the query engines at a transactor that you trust, which might be a node that you're running. All right, so one of the things, and let me check. Okay, it's already 8:20. So one of the things that we wanted to really show and focus on today here, and I'll jump to it, is, okay, this is all running, but I originally said this is for enterprise apps, right? And how do we really leverage this in our apps? And how do we do some of these things? So I'll quickly show you. We have an example app that we built. Let me take this out of, We call it Fluree Advocate. I'm going to show you some code for this, but just so you have a context for the code. All Fluree Advocate does is it allows a company to post announcements. Those announcements go into a topic, and if you're subscribed to the topic, you automatically get notified, and you can one-click share the company's post to your personal social networks. And what we do with those posts is then we track those shares so the company can reward the employees for helping to share. And because this has been on and off, let me just make sure I've got a good connection. So we generate these leaderboards here. This is actually a Fluree's instance of Fluree Advocate. So we shared out this post, and in this case, just Kevin and I shared it. But all the shares are tracked. And the FlureeDB is powering all of this information. So here I shared this out on Twitter. It's had 57 views, and here I shared it out on LinkedIn, and it also has a number of views. Let me jump. So here is the JavaScript code that's powering that app. And this is one of the things we really wanted to target with this database, is that we sort of incorporated the notion of how do we really do the type of development we do today with what's going on in the database. And anyone familiar with React or uses React? Okay, handful. So this is React. So this is JavaScript. And one of the things here that we have, in this case, this is the header that we're showing, and we happen to show the logo in the header. So right up here, there's a logo. That logo is configurable. And here's the component that's actually rendering out the logo into HTML. So it's rendering out an image tag, but you basically see that it's getting some sort of information. In this case, it's getting the URL for the particular logo. And what we've built is, because these query engines are actually separate from the transactor, we can make them really lightweight. We have built a JavaScript query engine that runs right inside your application. And you actually issue the queries to the JavaScript query engine that's running in your app. You're not issuing this to some remote server. And the query engine that's running right here with your app knows all the data that you're currently looking at and understands what data it doesn't have, and is going to go basically get index data that it doesn't have to render your queries. So here's the query that in this case is getting out that logo URL. This is the identical JSON format that we were just entering in the admin UI. So here we wrote out the query that we want. It's selecting, the ID of the company and the logo URL from basically this where this entity matches. And how we make this work is that we have a standard React component. We can use all the standard testing tools. It has zero dependency on FlureeDB. But we actually take this React component and we just wrap it with our query, and it will automatically inject the data right into your React component. So every UI component you build, you can just embed a query essentially right with that UI component, and we take care of everything. We take care of injecting the data right in there, rendering it, giving you status information if we're currently loading it or if it's already loaded, etc. And then, for example, here is the header component. See, anyone use React? Class header extends React component. Here in the UI is the header. You see this header has my name on it. It also has a bunch of menu options. So I'm an admin, so I get a couple extra menu options that other people who weren't an admin would get. But we need to figure out if I'm an admin. We also need to figure out my name. Oops. So here's the class. Here's our render method, which has a lot of HTML in it, but same thing. Here's our React component. Here is the FlureeQL query that gets specifically the data that this UI component needs, and automatically again injects it right in there so that we can just render it. And the cool thing is that a bunch of these queries and a bunch of these UI components, there's probably a bunch of them that are asking for my name. The local database engine already knows and consolidates all these queries together and ends up actually just making a single request out to get the data it doesn't already have. And because we take it to this level, we actually have the ability to introspect these queries and actually know exactly what data they're looking at. So let me exit this here, full screen. And what this enables us to do is when we wrap these components with it, because we know what every single UI is currently looking at, we know what index and what data affects the queries, we can automatically push real-time updates to every single one of these components, and every single app you develop is automatically a complete real-time app. So in this case, I'll go to, this is tracking click-throughs. I'll go to my Twitter page right here. And here is the post that came from Fluree, that this whole application we're looking at is backed. You notice the URL here is actually pointing to Fluree, a URL shortener we have. And as I click on this, you'll see I currently have on, well, I'll scroll it up. I have 57 views on Twitter, and as I click on this, I'm running it over my cellular connection. Yeah, there we go, 58. And the developer did absolutely zero to make this happen because the query engine knows every single query, every piece of data that could affect your particular UI and will automatically stream you the information. Every single thing you do becomes real time. And I'll give you another quick example that we built to kind of demonstrate some of the things we do. This is just a quick app we built to actually manage a company's cap table and stock option grants. And we used it because this gets screwed up in everyone's companies, and people get really excited about what percentage do I own. And we wanted a good app that could show off the time travel capability. So here we're running this app. And as of right now, we have 32% of our option pool available. We've issued all these options. This is, of course, just dummy data in here. But we embedded a single UI component here that allows you to time travel the entire application. As far as this application is concerned, it is talking to the live database. I had to do nothing to the application to actually make the entire application be able to rewind at any point in history. And if I want to take this and, for example, go all the way back to, see, we got 32% of our pool available. If I want to go back to, July 15th, 2017. The entire application, again, the developer did nothing. Now rewinded to that point in time, and you see here I have more of the option pool available because obviously a lot of those transactions hadn't happened yet at this point in time. So even for things like where people want like analytics or reporting pages, but they want the ability to report on what happened in 2017 and 2016, as a developer, you're creating all these like extra SQL tables often to try and store this historical data so that you can produce these reports. And with this capability, you have to do none of that. And the kicker is you have every single piece of relational data that existed at all these points in time. So it really, truly gives you the ability to actually rewind the entire application to any point in time. Someone had a question. Yeah.
Because of the amount of JavaScript I see and the SQL being built to the JavaScript, is there any worries about injection attacks? I would say SQL injection, but it's not really SQL.
Yeah, so basically everything is signed with a specific token, and the only way to do that is if the token would be compromised. And if you're not even running it in that way, and we're just trying to simplify it so people can use sort of password management, which people are used to using for apps. In reality, what's really happening as these transactions go through, those transactions are actually getting signed with a public-private key pair. And in this particular instance, in our beta instance, we're actually just maintaining the public-private key pairs for you to allow you to log in with a username and password. But you could actually, if you wanted to maintain your own private key, you could actually sign your own transactions and send those in. And then we have the ability, just like a Bitcoin transaction, we know it came from you unless someone stole your private key.
It sounds like it's more secure.
Yeah, I would probably say that definitely to the right audience, but you never really, I mean, security is relative. But yeah, I would agree with you. Thanks for saying that.
That's your plan. That's your plan moving forward, is having everybody handle their own private key?
No. So if for an enterprise application, obviously having everyone in the company try and handle their own private keys doesn't make a lot of sense. So we give you a lot of easy ways of doing that. And in fact, we demonstrate, and how we have our beta available represents that. So we're doing all the private key management essentially, but when you log in, we know it's you, and essentially we're turning around and basically just signing that and sending it to the network on your behalf. So you don't have to know that. But if it's running in full public database, the full public mode, then yeah, you would, just like a Bitcoin, you need to know your own private key, you would also need to know it here. So I'll just point out one other thing, because we didn't get into the rules and the permissions that much in here, as far as how we ensure you can only update the data you're allowed to do that. If anyone wants to continue to stay, I just don't want to go over time. I'm happy to walk through some of that. We do use this on the query side as well. So you had a question about, can we do that permissioning on the query side? And if you're running this, again, as not public, full public blockchain, you can. And this has changed my life, because normally you build up a web application, you're building 50 API endpoints that are doing nothing but knowing it's you logging in, and I'm modifying some SQL query to make sure I only return the proper data. It actually gives you the ability to hand people essentially a direct connection to the database, because their database will only ever have the data they can see in it. Everyone has a unique set of data to it. So you don't need all these API endpoints. You only need one, a generic query side, and everyone's rules and permissions are automatically enforced in the database itself. This allows ideas like multiple apps and teams sharing the same database, but not having to implement their own security rules around it, because the data itself is secured. This allows the fun idea of being able to, put in your job description for a new JavaScript developer. Hey, we're going to let you, push code your first 2 days of work in here, because the customer's data is actually controlled in the database. There's literally like nothing besides creating a bug in your code, there's nothing that they could do to accidentally expose data they shouldn't. So why not let them push some code, if that's going to help attract developers. So again, we had to make that permission level work for this to work as a blockchain, but then we turn that around on the query side, and it really simplifies the development process, in my opinion, a lot, and I think increases the security of web apps, because what we see happening is I have 50 API endpoints all trying to enforce security, and I change something in the database, and I need to remember, which endpoints does that affect, and trying to update that. If we can actually have the data secured where the data lives, a lot of those problems go away. All right. Well,
Facebook came up with GraphQL, so don't they have a database, or is this a solution that you could work with Facebook on?
Yeah, so GraphQL is really an API language. So in fact, it's not even really a query language, although a lot of people try and jam it into a query language, and it happens to align really well with how we structure data. But to implement GraphQL, what you're typically doing is you're working with a relational database or maybe a document database. You're still having to set up an endpoint and define essentially each of the graph query nodes, and then turn those into real SQL queries kind of behind the scenes, and then aggregate all that data together on your app server, and then send it back. So it is a lot easier from the app developer standpoint to interact with, but it actually puts a huge amount of burden in the application tier, which is now issuing still maybe 15 queries, stitching it all together, and then returning it. Because of the graph database nature of this, that's just how we return queries anyway. You don't have to do any work or any extra work to do that.
But could you work with other databases like MongoDB or something like that, or this is actually a replacement?
No, but if you had built a GraphQL interface in front of MongoDB, you would potentially be able to swap in FlureeDB for MongoDB. And not change your front-end app at all. Yeah. Any more questions?
I see that you reserved a GitHub project, but it's empty right now. Are you going to open source this sometime?
Oh yeah, great question. So yeah, this database will be completely open source. When we open source it, so sometime between Q2 when we release our full, we're out of beta and we do the full federated mode, mode of the product, and Q4 when we do the full public version. So sometime between Q2 and Q4, it's completely open source. You can run the database. It's free. We'll, of course, for companies that are trying to run a bunch of it, we'll, of course, be selling support services and maybe some certified versions that limit the company's indemnity, you know, so they have someone to go to if there's a patent lawsuit or something like that, which obviously you can't do with open source. So that's how we make money around it. And we anticipate building a lot of more advanced management tools around the databases itself as well, which we think companies that are running it in serious production environments are probably going to want a set of tools around it that give them more visibility. And we'll sell those sorts of tools. But the database itself will be free. Anyone can run it. Yeah?
So for enterprise businesses, if you evaluate the product, you've got the timeline that they should be looking at, Q2, Q4.
Yeah, so for enterprises that want to run it in this kind of federated model, end of Q2. And again, we have a beta version for free right now. Anyone can sign up on our website, and you can actually start using it. We put some, it's a shared environment, so we put some throttles on it. But we have some people who are using it today, even I think in some production kind of stuff. We don't advise that, but yeah.
I have a question of generic, or
Yeah.
I'd ask that if you could ask some general questions and stuff like that.
Yeah.
So a typical blockchain application, let's say that it is actually trying to create a content management and content sharing and social networking type of functionality. And they are basically rewarding the users in that blockchain environment and tracking identity of, you know, who are the people who have contributed or something like that. So in that situation, the part that would run in Ethereum would just be the smart contracts, but the rest of the application has to run on the cloud somewhere, right?
Yeah.
So only the very small piece, which is contractual, where multiple parties need to agree in certain degree of agreement or truth needs to be maintained. But the bulk of the rest of the application will run just like normal.
Yep.
You know, you would run LinkedIn or any other application on a cloud or something like that, right?
That's correct.
Okay.
That's correct. And you know, one of the things, at least our viewpoint, and of course we're biased, is that ultimately the part you want the blockchain to control, you know, when you kind of narrow it all down, it's some sort of state change. So you want it to maintain some sort of state that it guarantees of information for you. And we just think a database is, I mean, this is how we kind of do it today. So this is just, we think, a very natural place to do this. So one of the things that I think we will see a lot of is people going to Ethereum and writing smart contracts today. Well, if the database actually controls what's allowed from a state change standpoint, you can actually write that business logic in Java, JavaScript, Python, whatever you want, because the state change source is the thing that's controlling that integrity. So we think there's going to be a lot of situations where people are maybe going to Ethereum to do this, and it's like you don't have to learn Solidity, you don't have to like learn a new language and how you're going to stitch it into your current app server. Just write your business logic in Java. Just make sure those rules that you would want enforced are maintained at the data layer, and then you're free to use whatever tools you currently want to use. So there'll be things that obviously fit really well in the Ethereum world as well, but I think there's going to be a lot of things where it's like, I hope we give people the freedom of using, again, I started out saying we want to make this blockchain technology accessible to companies, easy for them to start to use, and right now it's not easy.
Well, I think that's what Microsoft's trying to do. I heard one of the presentation, and they're basically building that layer where you could, you know, define your smart contracts, and behind, you know, you could run it on, you know, Ethereum as a blockchain or something else. I don't think it's hyperledger quite, but
yeah, it's, you know, sort of a meta layer on top of different blockchains to kind of do that. Yeah, I mean, my opinion is at least a big chunk of it is sort of flawed to begin with. So building a meta layer on top of that, you know.
so
And again, I'm biased, but like, why? If you could control that at the data tier, where you're really controlling the state of your applications anyway, that's how we're used to building apps. That's how we've been doing them. Then that I don't see a good reason to change.
I'm curious about this question. Let's say that I have some transactions on Ethereum. I have invested something because it's on a public blockchain. If I'm actually one of the nodes in that, could I actually get that ledger and kind of spot my transactions in there?
So there's two parts of it. So the question came up. There's really two parts of it. For you to create a new block in Ethereum, you not only have to process the transactions, but you also have to be the first person to solve the proof of work puzzle. So that's really, really hard to do. So you would have to get very, very lucky that you did the both. But then as soon as you broadcast that out, assuming the other nodes are participating as they should, they'll be validating that transaction. And if they see something like a double spend or something like that, they'll end up rejecting it. So not really. Yeah, I mean, if your question was, can you sort of get control over that and put it?
But can I see my transactions in there? Can I
Oh, yeah, you can see your transactions.
Because they're in a public ledger, so I can see that.
Absolutely.
My transactions.
Yeah. In fact, what you can't do is not see your transactions because you see everything.
You see everything.
Yeah.
So this kind of a public blockchain would be good for projects which are actually maybe like a open social network or something.
Yeah.
Whereas the private ones would be like for supply chain, which maybe
That's right.
shared between 20 different companies and all that. But they need to create enough nodes in order to create consensus, right? I mean, that still needs to happen.
That still needs to happen. Yeah. And so if you're launching, in our case, if you're launching a database and you're trying to have the globe essentially or a huge number of nodes mine it, you have to provide enough economic incentive for them to get to the sort of consensus level that you want to.
So some of these miners are going to be sitting on both public and private,
Yeah, not necessarily the miners, but how we see it is that they're all part of the same data, or potentially part of the same database or data set. Your applications are talking to this query engine. You're not trying to query some unknown nodes in the cloud. You want to query a server that's sitting next to everything else you have. You get millisecond response times, et cetera. Why not let that piece aggregate the data together from these different data sources and provide it as basically a unified kind of source to you. So that's really our approach to it, but I'm not saying it's right. It's just, I think it's right, but I'm sure others will disagree.
So I have what I hope is a pretty general ops question and a pretty general security question.
Yeah.
From the general ops side, I thought I heard you say during your presentation that it scaled as a function of the number of nodes. So I thought that
I didn't say that, but
maybe there's a function, maybe there isn't. That was the first question.
yeah.
And then the second question about security was, you alluded to the fact that there's some kind of declarative language for setting up access control, and obviously that's got to be tied loosely, or probably tightly with the schema. And my question about security is like, who owns the schema access control rules, and how do they maintain ownership or authority over that?
Yeah. Yeah, there's actually a few really good questions. I'll even add to it a little bit in there, which is I talked about a language essentially controlling access in there. Who maintains it? How's it maintained, and kind of where do things go from there? And really the question is, how do you evolve schemas, which we need to do, but when you're running it in this completely federated model. So how it would start would be the same way like an Ethereum smart contract would start. Multiple organizations say, maybe they even have a legal paper contract. They say, this is what we agreed to. Now someone needs to take these rules that we decided on, or whatever it is, and actually put them into code. And everyone has the ability to audit that code and say, yeah, we agree, this reflects these rules we agreed to. And therefore, I'm going to participate in this node because I agree with it. So that's really how things would start. It's not, so yes, someone has to set up the rules, but of course you have all the people who are going to be involved in that. They can see the rules and they can say, no, that's not what I agreed to. I'm not participating in that, for example. How do we evolve it? So we have a notion of voting in here, and we have a prescribed way that we suggest you do it, but it's actually just using the database data. Like if you were going to build a voting app, you would structure some sort of schema in the database that would control who's voting yes, who's voting no, etc. So we have a prescribed way of doing it. You could actually veer from that if you wanted to, but you have the ability to stage changes and then link accounts or auth records to that and set up some sort of condition, again using the code, that say once 50% or 80% of these entities that are linked to this agree, commit through this transaction. So if you're evolving the schema or the rules, you can actually put that in place, but the database will not pay attention to that until these other conditions are met, which amount to a vote. So you may have a bunch of these changes actually staged, and maybe I'm running this with 20 companies, and only when 80% of the companies vote yes, does that particular rule change end up going in and actually taking place in the database. And if they don't, it keeps running the way it's currently running. There's a bigger question about immutability and schema changes. So if I can't change anything, what if I had a schema issue or some sort of rule? And one of the things you might have noticed when we gave the transactional results back, it didn't actually have like the attribute name in there, it had some integer in there. And so the attribute names that we're using and that you use from the app, like person email or person name, they're actually aliases to an underlying attribute which holds an integer identifier. And if something happened where you could not evolve the schema on that, you could actually create a new attribute. It is a new attribute at that point. The old attribute doesn't go away, but you can take that alias and point it to the new attribute so that none of your apps have to change. The data is still immutable. All the data is still there, but technically you're actually using a different attribute at that point under the hood than the original attribute. But the integrity of the database is always, always there. You literally can't change anything. There's also the thing of what about when you really need to change something? Database names, how you refer to them, are also aliases to an underlying integer that represents that database. We give you the ability to fork a database at any point in time. So you could fork, you can't change that original database. It's database number 202. I can fork database 202, create database 203 at any point in time, replay the fixed transactions on top of it. Now 203 has complete integrity, and actually change the alias. Say I called this Brian's DB, change the alias to now point to 203. 202 doesn't go away. It is still there. It still has all of its integrity. So that is one potential way of, if you had something you really had to get rid of. Now, if this is on the true public blockchain, you can never get rid of it until people in theory stop mining it. But if I'm running this with a group of 20 companies and we now move to database 203, we can all sort of agree, okay, we really don't need database 202 anymore, so let's just agree to delete that.
If you fork it from a time in the past, can you fake the transactions from that point forward?
You can apply new transactions from that point forward, but essentially they can be the same transaction sans whatever issue happened that were in the old database. But it technically is a new database at that point. It's not the old database. And the old database exists until you can somehow dump the storage, which you have the ability to do, but again, only if you control the storage, which in the full public blockchain, you don't control the storage.
So that's all pretty cool. The ops question about scaling the transactor?
Okay, scaling the transactions. So I mentioned before sort of 1,000 transactions per second is the kind of guidance we give around what our core transactors can handle. We're not really happy with that. We'd actually like to be able to scale it further, but we're kind of getting into an area of that we're pursuing and may or may not be part of the public blockchain. But it's the idea, instead of really a linear blockchain, we're using a DAG, a directed acyclic graph. And we're allowing transactions to happen in parallel. The problem is you don't really get quick finality. So you have to wait to some point afterwards that will end up resolving conflicting transactions to determine what happens. I know of node databases that use this type of technology. I wish I knew of some. If anyone knows of some, I'd love to look at them because we'd like to see what sort of things are working or not working. We have some very early models that allow, as long as we keep these graphs from getting too wide, we can actually achieve finality. Our calculations have it in between 4 and 5 seconds on a global network basis. But the idea would be that you could process database transactions in parallel across potentially thousands of computers, but things need to get built on top of that, and potentially in as few as 5 seconds, you would have a high degree of probability that some transaction you submitted isn't going to end up going away. That is a way of scaling a database potentially globally, really allowing n number of nodes to process transactions in parallel, but using part of these graphs essentially to reconcile things in the future. So it's an area we're very interested in. We're currently working on it. It may or may not be part of that kind of public blockchain. If it's not part of that public blockchain, we're sort of at that 1,000 transaction per second kind of threshold. If it is part of that public blockchain, then we should be able to actually scale it to even much higher levels. Now, you still have to deal with the synchronizing data and synchronizing large amounts of data across the globe. It's physics. It takes about a second to reliably get information from one side of the globe to the other. And when we think about databases, we're usually thinking about pretty quick stuff. Yeah.
Somebody installs this, what's the recommended machine image?
It's the database is in Java. So it's a jar file, and like I mentioned, it wants to run basically as an in-memory database. So the more memory you can give to it, the better. The less memory, basically what it means is it's doing more swapping of index segments. 2 gigabytes of memory would probably be the minimum, and if you have a big database with a broad set of hot data, the more memory you can give it, the better, because it can keep more of it fresh. Especially most application databases, they have pretty well-defined hotspots of the data. And as long as your hotspot data of your application can fit within whatever memory you give it, it will basically run about as fast as an in-memory database would. But if you have queries that are spanning, across every single index all the time, then essentially that's where things are going to start slowing down, because it's going to have to go and get index segments essentially it doesn't have. Where does it store the index segments? We have a pluggable storage backend, so it can store it right on disk if you want. However, one of the things we really wanted to promote is to allow you to use any sort of cloud storage to be the backend. So there's a protocol there. We expect other people to add additional backends, but before we ever confirm a transaction, the backend is responsible for telling us we have this durably stored and we trust that backend. So we have 2 that we currently ship with. One is, well, we're not shipping yet, but we have 2 currently built. One is backed just by an attached hard drive or network file system, whatever you want to do. And the other we've actually backed by Cassandra. Now, it's not using Cassandra as a database at all. It's really using it as a simple key value store. But Cassandra's got some nice characteristics that allow us to get these segment data in and out, and you can just throw more nodes at Cassandra, and it's really reliable. You could back it by S3. S3 is a little bit slow, but we'd like to put an S3 backend on there as well. But again, it's really up to that backend storage. It just needs to support about 4 or 5 operations to act as a backend storage, and it needs to be able to say, I stored things durably. Yes?
Question from a vulnerability management perspective. If there is any security flaw or a vulnerability identified, how is it, because there are going to be many public-private sort of scenarios there. So how will you push? Is there any auto-update or for the patches, how is it going to work?
Yeah, as long as, well, to answer that, so the question for everyone is, if there's a security flaw in the code, how do we get that out there? And of course, as open source, we'll publish a new version and communication about it. Where the complication comes in, and we need to kind of look at current blockchain projects for this, is that if that flaw determines that the protocols itself that run the database need to change, it means that the people mining the database have to agree and switch their software. And in a lot of cases, that happens very successfully. In some cases, you end up with these hard forks, where some people say, no, I don't agree with that change. I'm going to keep mining the old code. And some people go off and start mining the new code. And essentially, you have 2 versions of the database running at that point in time.
Could this run on a Filecoin, which is like a blockchain database or storage blockchain-based image system?
Those are a little bit more like object storage. So, you know, more if like what you would use Amazon S3 versus using MySQL. You know, kind of two different.
There's no SQL, just storage, right? Just raw storage, basically?
Oh, would the backend storage work on something like that? Potentially. You know, the key with our backend storage is we're really hoping to get index segments out into the query engines in under 10 milliseconds. Cassandra does that really good. You could do something like run, and this is one thing we're thinking about, is run something with a Filecoin. So Filecoin is like, you know, it's slow, and you don't even know where your data is. This could be all across the globe. But there's no reason you can't put a Redis or a Memcache in front of it. So as long as the segments that are coming in and out are sitting in Redis or Memcache, then of course you're going to be sub 10 millisecond. And in the case where that index segment isn't actually there and maybe it's being stored in Filecoin, you might have to wait a minute, you know, to get your query result. But so there are strategies where you can put a caching layer, because these indexes, they're immutable. They'll never change. So they're very easily cacheable.
Yeah, because it's supposed to shave your storage cost to 1/10 of what you pay like Amazon and all that. That's what they claim.
Yeah, but you know, Amazon has 4 or 5 different storage options today, and they're optimized to different things. If you want to save a lot of money but have slow retrieval, you can use Glacier, which is like 1/10 of what you'd pay to S3. S3, you want more response time. So, but yeah, I agree, but I don't think that replaces S3. Maybe it competes against Glacier or some of the more cold and expensive storage options. Yeah.
Does this change how you back up the data somehow?
I think it makes backup simpler. For one, you don't necessarily have to worry about the traditional backup and restore for databases, because I need to restore my database as of a month ago or a year ago, because you can query your database as of a month ago or a year ago instantly. So the only thing you need to back up is essentially the log file, that set of immutable transactions, because from that set you can recreate any database whatsoever. And again, being immutable, it's sort of easy to know what's successfully stored or what isn't stored. But yeah, I mean, you still want good, durable, backed up storage. You can just forget about the requirement of, I need that backed up storage because I have a business requirement that requires I can recover the database at any point in time over the last month. So now I have all these snapshots that allow me to do that, and we don't need the snapshots, because you can query the database instantly for every one of those times. It doesn't eliminate it, but it changes it. Cool. Well, thanks everyone. I really appreciate your time. Feel free to sign up for a beta if you want to play around with the product. We have a queue in the beta, but we're turning on accounts as quickly as we can. And if anyone has any more questions, feel free to reach out. Thank you.